Advanced Installation Issues. In this nugget, we're going to discuss a couple of advanced concepts: RAID and logical volume management. RAID has to do with organizing multiple disks or partitions on disks for a higher performance or higher reliability or both. Logical volume management gives a system administrator a set of tools to help them manage disk partitions, basically. So put on your thinking caps and let's get to work. Well, what is RAID anyway? Well, RAID stands for Redundant Array of Independent Disks. Sometimes you'll see the acronym Redundant Array of Inexpensive Disks. They both describe what RAID is. Basically, back in the early 90s when RAID was developed, there was an increasing need for large hard disk storage capacity. Okay, we were taking on projects like the Human Genome Project, or SETI, which was searching for extraterrestrial life forms in space. Okay, so there was just a need to hold large amounts of data on hard disk. Okay, so what were the options? Well, one option is to just build this mammoth, gigantic disk. Okay, the other option was RAID. All right, and the way that RAID works is instead of having the one large mammoth gigantic disk, we're going to have this whole series of these cheaper disks, these inexpensive disks, and they're all going to operate independently. All right, well, why would we want to do this instead of just build this one mammoth disk? Well, one reason we want to do this is for increased bandwidth. Okay, so each of these disks has a bus that's leading back to the processor. Maybe it goes back to they all go back to a controller first, then the controller leads to the processor. But the idea is that each of these disks can be transferring data simultaneously and independently of the other ones. Okay, so the amount of data that can be flowing back to the processor is increased. So the bandwidth from the disks to the processor is larger than in this system that just has one bus back to the processor. Okay, so there's increased bandwidth in the RAID system. There's also lower latency. Latency is the amount of time you have to wait to get your data off the disk. All right, so when we go to ask for something off this disk, how far away is it? Well, it's at most 1 revolution away. That's the same for this disk. It's at most 1 revolution away. However, these smaller disks can spin faster because they're smaller. Okay, so because they spin faster, 1 revolution is faster, and so the amount of latency on these smaller disks is smaller. Okay, that's another reason we like RAID. The other reason that we like RAID is that we have an ability to recover from disk failures. If we set up these disks smartly, and I'm going to show you what that means in a second, any one of these disks will be able to fail, and we'll still be able to recover all of the information on there without going to a backup, without going to like backup tapes. Okay, all the information is actually going to be out here on the hard drives, and we'll be able to, substitute in a new disk and copy information from these other disks over to this new disk, and we're going to be back up and operational. Whereas if this disk fails, then we have to go and back up this whole disk, and this is a mammoth disk that's going to take a long time to restore. Okay, so so here we have an ability to recover from disk failures more quickly and more efficiently. All right, so that's the basics of what RAID is. Now let's describe it in a little bit more detail by describing these different levels of RAID. So I want to describe to you RAID level 0, RAID level 1, and RAID level 5. In theory, there's actually like RAID level 0 to RAID level 10, but in practice, these are probably the 3 most common ones and the ones that are actually supported by Linux. Okay, so first let's talk about RAID level 0, which is also called disk striping. Now, disk striping is we're going to have our little array of disks. Let's just say we have 3 disks in our array. And we're going to take some file F. When we want to write that file F out to disk, we're going to break it up into chunks, and we're going to write this first chunk on disk 1. Then we're going to take this second chunk and write that on disk 2. We're going to take another chunk and write that on disk 3. Then when we get to the 4th chunk, we're going to write that back on disk 1. And the 5th chunk, we're going to write here on disk 2. And we're just going to continue this until all of F is written out to the disk. Okay? So by striping data across disks, you're getting that increased bandwidth because we can do this writing and reading simultaneously and independently. Okay, so you're getting increased bandwidth over the one gigantic disk. You're getting improved latency. So when we want to go and read this file from disk, the disks, because these are smaller, they're spinning faster. So we're getting the performance increases of RAID with RAID level 0. We're not getting any ability to recover from disk failure, though. Okay, so if this disk failed, I've just lost the file F, right? Because some piece of F was written on that disk, and I won't be able to reconstruct it from the information that's out there. Okay, so I will not be able to handle disk failures in RAID level 0. I'll have to go to backup tapes, and if this was just written a couple seconds ago, then I won't be able to recover the file F off of the disk. Okay, so that's where RAID level 1 comes in. RAID level 1 is also called disk mirroring. So for every disk in RAID level 0, we're going to make 2 disks in RAID level 1. Okay, so for each of these disks out here, we're going to have 2 disks. These 2 disks are really just mirror images of each other. That's where the name mirroring comes from. So when I write this first piece of file F, I'm going to write it to this disk, and I'm going to write that first piece of file F also to this disk. So these 2 disks will be synced up. They'll be simultaneously updated, and they will be mirror images of each other at all times. Okay, so if any one disk fails again, so we've got our whole little array out here. Now if this disk fails, well, who cares? We've got this disk that's an exact duplicate of it. So this disk failed, we unplug it, we plug in a new one, and then we copy all the data from this one over to it. Okay, and now we're back up and we're fault tolerant again. And we were never down. There was no downtime at all because this disk could just fill in anytime this disk was being written to as part of the pair. Well, forget it. That disk is out of the picture, and we'll just write to this disk. And when we get the new one in, we'll copy all the data over, and then we'll be back up in action. Okay, so that's disk mirroring. Now this might seem excessive, right? That we have 2 disks out here, essentially for every 1 disk of actual data that we have. But it just depends on what your data is, right? If you're talking about some critical database application, or you're like a bank, some Swiss bank that's doing $1 million transactions, you can't afford to lose information about some transaction. Okay, so you need to make sure you have this fault tolerance or this redundancy. Okay, now RAID level 5 is a sort of an improvement on RAID level 1. We'll have fault tolerance in RAID level 5. We'll be able to recover from any error to any disk, but we do it in a smarter way. We do it with what's called a parity disk. So we'll still have our 3 disks out here of data. But instead of having a duplicate of each one, we're going to have 1 disk out here that we'll call the parity disk. Okay, now it doesn't matter how many disks are in our data bank. We could have 3, 10, 100, it doesn't matter. We'll still only need 1 parity disk to do it. Okay, so let's just play this game, right? So let's just flip coins heads and tails. All right, heads, and tails. Okay, and then on my parity disk here, I'm going to keep track of whether there was an even number of heads or an odd number of heads. So I'm going to write even here. All right, now I'm going to erase one of these. Okay, you can't see it anymore. All right, well, what was it? Was it a heads or a tails? Well, you see a head, you see a tail, and you know the number of heads was even, so that must have been a head. Okay, that's the way a parity disk works. It keeps track of the information on there, zeros and ones, and it keeps track of whether there was an odd number and even number of ones out there, and it can reconstruct the information. So when this disk fails, we can reconstruct the information from the other 2 disks and the parity disk. Okay, that's a real brief overview, and this is actually, the way I just described this is actually RAID level 4, okay, but RAID level 5 is a slight tweak to this. You don't really need to understand the differences for our discussion. Okay, so these are the 3 levels of RAID that are out there, and now let's talk about the differences between hardware RAID and software RAID. So hardware RAID means that we've got this array of disks out here, but more so it means also that we have a controller for our RAID array. So all of these disks are hooked up to a RAID controller, and then the RAID controller is hooked up to our processor, our computer. Okay, so to the processor, it looks like there's just a single disk on the system. So when that processor wants to write file F out to disk, it writes it out and it gives it to the controller, writes file F out to the controller, and the controller worries about taking file F and striping it across the disks. The controller worries about mirroring information from file F to other disks if we're running RAID level 1. The controller worries about writing information to the parity disk if we're running RAID level 5. So the brains of the operation is all out here. So needless to say, this controller can be very expensive because it's got a lot of stuff built into it, a lot of logic built into it. Okay, and typically these systems are SCSI systems, and so they're more expensive there too because all the disks are SCSI disks. Okay, so that's what hardware RAID is. You get all the performance, you can get the fault tolerance if you're running RAID level 1 or RAID level 5, but to the processor, like I said, and to the programmers, it looks like there's 1 disk on the system. Software RAID, on the other hand, all the brains of the operation or the logic is actually in the kernel, the Linux kernel. Okay, so here our picture for this one is going to be, here's our processor, and here's, let's just draw out 2 disks for simplicity, and say we're just running RAID level 1 and these 2 disks are just mirror images of each other. Well, instead of this processor, giving file F to a controller like it did here, the processor says, okay, I'm going to write file F to this disk, and I'm also going to write file F out to this disk. So the logic, the RAID logic, is actually in the processor. So the processor is more burdened here, right? The processor generated 2 writes to 2 different disks. The processor here just generated 1 write, it gave it to the controller, and the controller dealt with all the extra stuff. All right? But today's CPUs are really fast, and they typically have cycles to spare, meaning that they're not busy every single moment. And so generating this amount of extra information inside of the kernel might not be such a burden, and typically performance can be excellent in such a system. Okay. Also, because the logic's in the kernel, these disks out here can be IDE disks or SCSI disks, whereas typically these RAID controllers are only SCSI on a SCSI system, and so we can get away with a less expensive RAID system. We can actually, I'm going to show you how to set up here in a second, we can actually have a RAID system on a single disk. So just say instead of having 2 disks on our system, we've got 1 disk. But there's some information on this disk that is very critical to us. Okay, just say it's, the /var directory or something. Logging information is very critical to our system. And so we want to have a live mirror copy of that information. Okay, well, so what do? Well, we make 2 partitions on this disk, and we set up a RAID, software RAID system on these 2 partitions. So they're going to be mirror images of each other. So now, when the processor wants to write file F out to this partition, well, it writes file F out to this partition, and it also writes file F out to this partition. And so, this is a RAID system. This is RAID level 1. The 2 partitions are being mirror image. We only have 1 disk in our system, but we found this information, this data in var to be so critical that we want it to be mirrored, so we can set up software RAID to do that. Okay, and I'm going to show you how to do that now from the Linux installation screen. All right, so that's RAID for you. The differences between hardware RAID and software RAID, remember, is that this controller has all the brains in it, and for the software RAID, all the logic is actually in the kernel. All right, now I want to show you how to make a software RAID device using the DiskDruid program in the Red Hat installation program. Okay, so we're going to select DiskDruid here. We got our classic warning about the device partition table being unreadable. We do want to initialize it, and then we get our partition table screen where we see that everything on our device is free space. Okay, so what we're going to do here is we're going to create new partitions. These new partitions then, once we create them, then we'll select RAID over here and make the new partitions part of this RAID device that we're going to create. All right, but first we have to make the new partitions. Actually, the first new partition that I want to make has nothing to do with RAID. The first new partition that I want to make here, I'm going to make for the /boot directory. And here's what's going on. If the /boot directory is part of a RAID device, you have some severe restrictions on what you can do with the RAID device. The RAID device cannot be a RAID level 0 or a RAID level 5 device if the /boot directory is contained in it. Why is that? Well, if the /boot directory is part of a RAID level 0 or 5 device, then it would be striped over multiple partitions or multiple disks or whatever we have, and that would be bad because when the system boots up, the /boot directory is expected to be in a particular spot on the hard drive. And if it's striped over multiple partitions or disks, it's not going to be found and the system's not going to boot up. Okay, so the safest thing to do is to make the /boot directory in its own partition like we have, well, like we always have up until now. Okay, so I'm going to make the /boot directory an ext3 file system. I'm going to make it 100 megabytes big. Okay, and then I'm going to select OK. And now you see it shows up in our partition table, just like it always has. All right, now I'm going to make a couple other new partitions that will be for our software RAID device. All right, so now you don't pick a mount point for these partitions. And the reason is because the partitions are not going to have a mount point. Once we put the partitions into the RAID device, then the RAID device will have a mount point, and we'll see how to do that in a couple seconds. All right, so I'm not going to select mount point. Instead, I'm going to come down to this file system type and select software RAID. And you can see when I selected that, the mount point became not applicable. Okay, so software RAID is chosen. Now I pick a size. I'm going to pick a 750 megabyte partition size for this partition that I'm creating, and then I'm going to say OK. All right, and now it shows up in the partition table. It turned out to be 753 megabytes big, and there's the type software RAID. Okay, you can't see it all, but it's a software R. That's what it means. Okay, so now I'm going to select another new partition, create another new partition, and I'm going to do the same thing. I'm not going to touch the mount point. I'm just going to come down to File System Type, choose Software RAID. I'm going to make it exactly the same size, 750 megabytes, because I'm going to make these two partitions mirror each other. All right, and if they mirror each other, they should be identical size, because if one's bigger than the other, the smaller one's going to fill up first potentially and cause problems. All right, so I do that, and I'm going to select OK again. All right, and now you can see two partitions in my partition table, SDA2 and SDA3, and they're both of type software RAID. Okay, now I'm going to come over here and select RAID, and when I select RAID, I'm going to get a new screen that says Make a RAID Device. All right, now this RAID device will have a mount point. We'll pick a file system type for it, and we'll also pick the level of RAID that we're going to do. All right, so I'm going to pick /var to be my mount point. All right, maybe for your system it makes more sense to have /home be that mount point, or just / or whatever you want. Okay, ext3 file system, I'm going to choose RAID level 1, and I'm making sure that SDA2 and SDA3 are both members. They're both starred there, so they're both members of this RAID device. All right, now I'm going to say OK. And now you can see RAID device 0 shows up. This doesn't mean RAID level 0. It's just that RAID devices start counting at 0. So it's like 0 is the first one, 1's the second one, 2's the third one, and so on. Okay, so RAID device 0 is there. It's 753 megabytes big. It's an ext3 file system in the mount point /var. All right, that's the way it appears sort of at the highest level. But underneath, it's made up of these two partitions, SDA2 and SDA3. So even though it says it's 753 megabytes big, well, that's how much stuff we can write to it. But really, that's going to take up twice as much disk space, because every time we write something to /var, it's going to be written to partition SDA2 and SDA3. Okay, so does this make sense to you? The thing here is that you don't really see that these two partitions are associated with this device. If you were doing a graphical installation instead of a text installation, over here, the screen is basically the same information, but it would say mount point or RAID device associated with it, something like that. And over here, this would say, for these two partitions, SDA2 and SDA3, it would say something like /dev/md0. And then up here for RAID device 0, it would say dev md0. So you would see that partitions 2 and 3 would be associated with this RAID device 0. All right. Normally, I advocate text-based installations just for some of the problems that come up with graphical installations and graphics cards and things like that. But this is one case, and we're going to see another case in a few minutes, of where a graphical installation is actually a little bit nicer because it gives you a little bit more information. So instead of showing you the graphical one, I showed you the text-based one in case you did the text-based one and you got confused or something. I figured I'd show you the confusing one and just clear it up for you. If you're doing the graphical one, there's just a little bit more information, and it should be more clear how things are laid out. Okay, so there's our software RAID device, and it's for partition 2 and 3. There's still free space left over on our hard drive, so we can do whatever we want with that. We can create another RAID device. We could make swap space and other partitions that are not part of a RAID device, just like /boot was not part of a RAID device. So we can lay it out however we want. Again, just remember that this partition here is really taking up twice as much space, so if you're going to make RAID devices on your system and do mirroring, you're probably going to need slightly bigger disks than you're used to for whatever you're using it for. Okay, so that's a software RAID device. And now let's move on and talk about logical volumes. All right, let's talk about logical volume management, or LVM for short. LVM allows you to manage partitions. So if you set things up correctly when you're installing Linux, you can make it so that if a partition fills up, you can expand that partition in a nice, neat way. You're not going to end up wasting disk space or having to add new disks or anything like that. Okay, this is new to Red Hat 8.0. Other variants of Linux have had this around for a while. Red Hat didn't adopt it until version 8.0. So let's talk about some terms and concepts for LVM. Okay, the first term is the physical volume, or PV. Okay, the physical volume is associated with actual hard disk space. Okay, a physical volume cannot span more than one hard disk. So if you've got multiple hard disks in your system, you're going to have multiple physical volumes. All right, this picture I have here is a 2 gigabyte disk in my system and a 4 gigabyte disk. All right, and these are the physical volumes. Actually, this whole 4 gigabyte disk is not part of my physical volumes because part of that disk is my /boot partition. So this is like a classic partition that we've done, just like in the RAID stuff. We didn't want /boot to be part of a RAID device. We also don't want /boot to be part of a physical volume. So /boot is going to be its own partition over here, let's just say 100 megabytes big, and then the rest of that stuff is my physical volumes. Those physical volumes then make up a logical volume group, which I've denoted here. Okay, so here this is 6 gigabytes big, because these disks were 6 gigabytes big, minus 100 megabytes that's used for the /boot partition. So this logical volume group is 6 gigabytes minus 100 megabytes big. All right? Now that logical volume group, we take and we break that up into logical volumes. All right? And those logical volumes that are out here are a lot like partitions, but they're a little bit different. So they have a mount point associated with them, like /home, a size, 1 gigabyte, and also a file system type, like ext3. Okay, so this is a lot like a partition. We're going to have a mount point associated with this logical volume that's 3 gigabytes big with the mount point of the / directory, the top level directory. We're going to have a swap logical volume that's 500 megabytes big. And then we're going to have a logical volume here at the end that's free space. Okay, that's going to be about 1.5 gigabytes. All right, and now what you can do is, this is your system setup that you did at installation. If one of these volumes fills up, or say you want to increase swap space, like you think that the performance is bad for the amount of swap space that you gave your system, well, you can use space from this free space pool over here and put it into these partitions. Now, this is not the same. Like, if we were just straight up partitioning our system and we left free space, we could not add that free space to one of these things if they were actually partitions. But because they're logical volumes and there's this logical volume manager sort of taking care of this thing, well, we actually can add free space from this pool into these partitions and just grow the partitions. We don't have to copy data from /home to somewhere else and redo things, which is what we would have to do if we didn't use LVM. All right, so there's the terms and concepts for LVM. Now I want to show you how to create a system using logical volumes from the installation screen. Then we'll move out to the Linux screen, and I'll show you how to update, take free space and put it over into home. But first, let's look at, from the installation screen, how to set up logical volumes from the beginning. Well, to set up logical volumes from an installation program, you're going to have to do a graphical-based installation. I know I always tell you do text-based installations, but if you're going to do logical volume setup, you've got to use a graphical installation of Linux. Okay, so I'm going to choose here to manually partition with Disk Druid. Okay, it brings up the basic same warning message that we've seen before. I'll say yes. And now, here it is. I've got free space out here, about 4 gigabytes of free space again. Okay, now what I'm going to do here is I'm first going to create my /boot partition. So I'm going to click on New here, and then I'm going to add the partition. I'm going to add all this information. So I'm going to pick an ext3 file system, the /boot directory. I've made it 100 megabytes big, fixed size, and so on. Okay, now you can see SDA1 is /boot, and it's 102 megabytes, and so on. All right, and this picture up here is like the picture of the disk. That should say SDA1 and 100 megabytes big, but it's so small it doesn't even fit in that little graphical window. Okay, so now I've done that. Now what I'm going to do is I'm going to create some partitions, and then we'll turn those into logical volumes. Okay, so here I'm adding a new partition, but now when I add the partition, I'm going to pick from this file system type list, I'm going to pick physical volume. Okay, remember that's the highest level in that picture that I just showed you on the whiteboard. Physical volume is what we're picking here. All right, I'm going to say, since I only have one disk on my system, I'm just going to say fill to maximum allowable size. I just want to fill up the rest of the disk with this physical volume, and then I'll break that physical volume into these logical volumes that will have mount points associated with them. Okay, so I'm going to say OK here. And now I've got this type as a logical volume manager, a physical volume in the LVM program. How big is it? It's the rest of the disk. It's the whole rest of the disk from 14 to 522 cylinders, like about almost 4 gigabytes big. Okay, minus the 100 megabytes that I used for the boot mount point. Okay, so I'm going to say okay, and now I'm going to click on LVM. All right, so when I click on LVM, then I get this Make LVM Volume Group. All right, so the volume group name, remember in that last picture on the whiteboard, the physical volumes went to a logical volume group. Well, since I only have one physical volume, so that's the only logical volume group I'm going to have is containing that. Then the interesting part is when we break this up into logical volumes. Okay, the physical extent here, don't mess with this kind of stuff because, there'll be a list here if we have multiple physical volumes to use. I only have one. They always make it in increments of 4 megabytes. Don't mess with that, okay? And then what I'm going to do down here is I'm going to click on Add, all right? And I'm going to say Make a Logical Volume. All right, so I'm going to associate a mount point, a file system type, the logical volume name, which I don't change. You can give these actual names if you want. I just would rather leave it the way that they do it, and a size associated with that mount point. Okay, I'm going to click on OK. And now I've got, under my logical volumes names here, I've got logical volume 00/home, and the size is 752. Now I'm going to add another one. Okay, and up here I'm going to say, let's make some swap space 500 megabytes big. Okay, and you can see the mount point is not applicable, which it shouldn't be for swap space. I'm going to say OK. All right, and now I do another add, and I'm going to have the mount point / be size, say, 1500 megabytes or 1.5 gigabytes. All right, then I'm going to say OK, and that's it. All right, now what did I do here? Is the free space I have left over is 1232 megabytes. You can see that in this diagram up here. Okay, that's okay. It's okay to have free space because when one of these things fills up, or if I want to just increase swap space for performance reasons, I can do that out of the free space pool. Okay, so now I'm just going to click OK, and now we get our picture here. Here is volume 00. The logical volumes associated with that are here, 0001 and 02. It's for / home and swap space. Tells you how big each of those is. And then down here under hard drives, it's telling you exactly what's going on. SDA has been broken up into 2 partitions. SDA1, which is /boot, and SDA2, which is this volume 00. Volume 00 is described up here, what it's made out of. Okay, this partition, SDA2, is 3,993 megabytes big, even though the sum of these volumes here doesn't quite add up to that. You'll also see that volume 00 is only 3,984 megabytes big, even though the partition's 3,993. Well, those extra 9 that we're missing here, that is some overhead associated with the logical volume manager. Well, that's it. That's all there is to creating logical volumes from the installation program. Now we'll move out to the Linux screen to see how we deal with managing these once Linux is already installed and we want to allocate space from that free pile over to one of these other partitions that we already created. Or logical volumes we already created. I have to smack myself on the knuckles for that. All right, well, what I want to do now is show you some of the commands that you can use to manage logical volumes. All right, we use DiskDruid in the installation program to create our logical volumes, but if you're going to do any management to those after installation time, you're not going to be able to use DiskDruid because that's only an installation program, so you're going to have to learn some of these commands. So the first thing I want to do is just look at the info page for LVM. So LVM, it just describes what LVM is, and if you page down here, you can see some of the abbreviations that are used. It's good to understand these abbreviations because a lot of the commands use these abbreviations inside of the commands. Okay, so if we page down further, you'll see some examples here on how to create a physical volume and a volume group, and then how to create a logical volume group once you do that. And then we page down further, and you can see a whole slew of commands here to manipulate logical volumes. Okay, so if you do things like add a new disk to your system and you want to make that physical volume, part of your logical volume group. Well, this is where you're going to turn to look up how to do this stuff, or these commands, and you can pretty much tell what each command does, right? Like LV create creates a logical volume, LV displays a logical volume, LV extend extends a logical volume, and we're going to do a command like this in a second when we go back out to the command line. Okay, and PV commands are for physical volumes, and VG commands are for volume groups. Okay, so if you need more information about LVM, because this introduction I'm giving you is definitely somewhat superficial, it's just like the beginning of the iceberg, go to Sistina.com and you'll see a how-to page there. Like www.sistina.com has archived news groups talking about LVM. They have information about LVM development and so on. So all the information you want about LVM you can get from Sistina. Okay, so there's the info page. Let's just go out and I'll show you quickly how to do an extension of a logical volume. So what we're going to do here is, if you remember when we created the logical volumes, we made the /home directory in volume group 00, and we made it 750 megabytes. Okay, well, we asked for 750 megabytes, and then, they made it like 752 or something like that, or 754 or whatever it was. And what we're going to do is we're going to extend that logical volume. We'll just assume like it's getting close to full, and we want to add like an extra 100 megabytes of disk space to the /home directory. So here's how we do it. We give the LV extend command, then we give a -L option, which specifies a size, and we say plus, I don't know, let's just add 100 megabytes. Okay, now if I said just, okay, what you have to be careful of here is that you put that plus in, because that adds 100 megabytes to the I want to say partition, but it's not a partition, it's a logical volume. So that adds 100 megabytes to the logical volume. If you leave off that plus, bad things could happen, especially if you're doing reduce. If you say reduce and you just give 100 there, then that will actually break it down to 100 megabytes instead of taking 100 megabytes off. So you have to be careful about the syntax here. Make sure you do it right. For extend, we want to put a plus there in the front. And then what you have to do is you have to give the path to the logical volume. So it's in the /dev directory. Then your volume group is the next directory. We only had one volume that we created, volume 00. And then you give the logical volume group. And for us, that was logical volume 00 for the /home directory. So now if I do that, you'll see it's extending logical volume 00 to 852 megabytes. Okay, and so there it says successfully extended. So now our /home directory has 100 extra megabytes in which to grow. Okay, and that was exactly the point of using logical volumes. It takes a little bit of overhead to manage that. You lose a little bit of disk space for that, but you get flexibility later on in how you extend these logical volumes, so because you might not be able to predict how your system's going to grow. Okay, so this is a good tool to get over some of those uncertainties about how your system's going to grow. All right, well, it's time to wrap up our nugget on advanced installation issues. We started by talking about RAID. We talked about the RAID levels, RAID level 0, 1, and 5, and how they were different. And we also compared and contrasted hardware RAID and software RAID. And we also set up software RAID on our single disk system so that a partition was mirrored on the disk for ultimate reliability. And then we talked about logical volume management. I gave you a brief synopsis of what it was. We set up LVM at installation time. I showed you a little bit about how you can manipulate LVM post-installation. And remember, there's extra info at www.sistina.com. All right, well, that wraps up this nugget on advanced installation issues. I hope you found this informative, and thanks for watching.